Partial differentiation comes to your rescue. Now, to solve this problem, partial differentiation will be really helpful. Now, the reason is, over here you can see that there's in the integrand we have a little bit complicated expression in denominator, which is again squared, right? And this square makes it a bit complicated. Now, how partial differentiation can be helpful is, so let's say if we first solve the another integral, which is basically the same integral without the square and denominator, right? Without the denominator being squared, just this. Then if we solve this one, if we now partially differentiate with respect to x or y, we are going to get squared over here, right? Using the quotient rule, or like just the power rule, we are going to get square over here, and we can make use of that fact some way. So let's see if we can or not. First of all, let's try to solve this integral, and then we will see how we will like get to this result from here. So to solve this one shouldn't be too hard, right? You can just divide both numerator and denominator by cos square x. That gives you integral from 0 to pi by 2. Sorry, cos square theta. So sec square theta d theta divided by x square plus y square tan square x. Tan square theta, sorry. Tan square theta. Now, if you let u as tan theta, our du will just be sec square theta d theta, right? So now the limits of integral will go from tan 0 to tan pi by 2, which is tan 0 is 0, tan pi by 2 is infinity, sec square theta d theta is du divided by, this is x square plus y square u square. Now note that since this integrand is in terms of u, x and y are just constants, right? Now basically I can just take 1 by y square outside. So this integral will go from, this integral will be u square plus x by y whole square, right? Now this is just the integral in the form 1 by u square plus a square, right? And we know that this is just 1 by a tan inverse u by a. Yeah, so this will also be 1 by y square times, this will just be 1 by x by y tan inverse u divided by x by y. So yeah, and then going from 0 to infinity, right? So this will be 1 by xy tan inverse uy by x from 0 to infinity, right? Now we know that when u is infinity, this will just tan inverse infinity, which is pi by 2. When u is 0, this is tan inverse 0, which is 0. So this is just pi by 2xy. You see that, right? Okay, this isn't too hard, I guess. So we got that this is pi by 2xy. Okay, the thing is, we got that integral from 0 to pi by 2 of sec square theta d theta divided by x square plus y square tan square. Sorry, this is an alternative form. Okay, we got that d theta divided by x square cos square theta plus y square sin square theta is just pi by 2xy, right? Now, okay, we want to get square in denominator, right? So what you can do is, let's partially differentiate both sides with respect to x. So if we partially differentiate both sides with respect to x, notice that if we are if we are partially differentiating with respect to x, all these other things, thetas and y's, will be constant. So in partial differentiation can go inside the integral, because integral is just a sum. So this will be d theta divided by, basically this is to the power of minus 1, so there will be minus 1 times this thing to the power 2, right? And then again, if we use the chain rule, now we have to differentiate this expression only. First of all, we just made that derivative of 1 by y is minus 1 by y square. We used, sorry, with respect to y, we used this fact, right? The derivative of inverse is negative 1 over x square, something like that. Now if we use chain rule and if we try to differentiate denominator, we will get 2x times cos square theta, right? So this is the partial differentiation with respect to x in this side. In the other side, pi by 2i will be just be constant, and we will have minus 1 by x square, right? The minus from both sides can be cancelled, so we get 0 to pi by 2, 2x cos square theta d theta divided by x square cos square theta plus y square sin square theta whole square is equals to pi by 2x square y, right? So I basically cancelled minus from both sides. Okay. Now if I had partial differential with respect to y, the only change would have been I would have got 2y sine square theta, and over here we would have 2xy square, right? So if I had, let's say, differentiated, so this is basically a partial differentiation with respect to x. Now if I had done, let's say, partial, like in this like original integral, if I had done partial diff with respect to y, then what I would have got is 0 to pi by 2, 2y sine square theta d theta divided by x square cos square theta plus y square sin square theta whole squared is equals to pi by 2xy square, right? That's the same thing. I'm just substituting x by y and y by x, right? Now over here, now how do I use these two results to find our original integral, right? What I can actually do is, again, since this 2x is just a constant in this integral, I can take the 2x outside, right? I can take the 2x outside, right? Over here. I can also take the 2y outside, right? Over here. Now, again, from here, I can also take the 2x to the denominator of other side, right? If I do that, this 2x will multiply over here. If I do the same over here, this 2y will be multiplied over here. So that means answers for this integral will be, now answer for this newly formed integral will be 1 by 4x cube y pi by 4xy cube, right? Now, since now these two integrals have limits, same limits, right? Same denominators, right? So if we add these two, what happens is just numerator will just be added. Sin square theta plus cos square theta d theta divided by x square cos square theta plus y square sin square theta whole square. And this is going to be the sum of these two results, right? So 1 by 4x cube y plus, pi by 4xy cube. Now we know that the sin square theta plus cos theta is 1, right? So this will be 0 to pi by 2 d theta divided by x square cos square theta plus y square sin square theta whole square. Now if I take the common pi by 4xy, I would just get 1 by x square plus 1 by y square, which is the answer. Wow. So the answer for this integral is, this is the textbook answer. So yeah, I'm just writing it in different form to match the answer in the textbook. So this will be pi by 4xy 1 by x square plus 1 by y square. And how we solved it? We solved a different integral, then did a partial differentiation with respect to x and y, manipulated the result, and then added the result to get the required integral. So this is how partial differentiation can be helpful to solve some integrals. Basically, like if the solution integral is differential of some other integrals, right? Just like over here, 1 by y square was like derivative of 1 by y. So yeah, if the integrand is derivative of some other functions, we can definitely integrate the other function and then partially differentiate it. This is also called Feynman's technique, right? And it's really helpful. So that was it for today, guys, and I look forward to seeing you in the upcoming video as well. Enjoy and do so with your friends.